Alright, so we talked about one application of derivatives so far, which was a pretty small one, but one that was nice. You can approximate values that you would normally need a calculator to use in linear approximations. The next one, which is going to be more what calculus is about in the real world, and this is going to be what a lot of the class is about, and that is something you may have already known, but that is position versus speed versus acceleration. So let's say that the position of an object was called S of t or something like that. So actually, I should probably just call it P of t, right? Because it's position. If the position of an object on a x line, aka an object moving back and forth, this is an equation where you put in a time, it'll tell you how many feet away something is. That is a position versus time line. The derivative of position versus time is actually the velocity at that time. And you can think of it like this. If this right here is your position versus time graph, well, this is what it looks like. The slope of it, rise versus run, equals wait, what am I doing? Sorry, I was really confused for a second. Will be P and T. So rise versus run in this case would be P over T, which is distance over time, which is the same as velocity. Therefore, because we're doing a derivative is the slope of a line, the derivative of the P versus T graph is actually velocity. And we're usually going to call that V of T, where you put in a T value and it tells you what the speed is at that moment. Now, the derivative of the V versus T graph, which also it would be called the double derivative of the position versus time graph, this is the acceleration graph. If you've taken a physics class, you would know that acceleration is usually marked as meters per second squared. So if we're doing a velocity versus time graph, looks like that, then the slope would be velocity over time, which is, we'll just call it meter per time, which is meters per time squared, which is acceleration. Knowing this, we can actually start interpreting graphs. This video is going to be very basic, but I'm just going to talk about what you know from looking at a graph. So let's say right here, and this will be further elaborated, I believe, in the next unit, but let's say right here, this is the, let's do velocity versus time graph, and it looks something like that, or something like that. I don't know. Whenever this graph equals 0, that is like saying that the position graph slope is 0, right? Because the position, this is the derivative of position. And for that reason, whenever the velocity is 0, or I'm sorry, that means that, as you know, can interpret from this graph, that whenever it equals 0, the velocity is 0. But let's take right here, at these points, the minimums and maximums, which we're once again going to talk about a lot more next unit, the slope of these is 0. So that means that if you were to draw the derivative of this, these would now be here because they would be 0. And for that reason, in an acceleration versus time graph, if something is touching 0, that means it's not moving, and the velocity, or that means that it's not accelerating, and that the slope on here. So basically what I'm trying to say is that the minimums and maximums mean something in this graph. The maximums and minimums on the velocity versus time graph is when the acceleration is going to be 0, because they're all related. I hope that makes sense. And if it doesn't make sense, then don't worry about it, because this is going to be much further elaborated later, but basically you just need to know that acceleration versus time is the same thing as the derivative of speed versus time, which is the same thing as the double derivative of position versus time.